Albert Einstein, a man without a middle name but never without groundbreaking ideas, revolutionized our understanding of the universe with his profound theories. Einstein was not one to settle for mediocrity or leave anything to the middle. His work has left an indelible mark on the world of science and beyond. From reshaping our understanding of time and space to altering how we perceive light and energy, his insights have become the foundation of modern physics. Einstein's theories, such as the iconic equation E equals mc squared, echo through the halls of every classroom and university worldwide, encapsulating the astonishing equivalence of mass and energy. Yet not all of his contributions received the same level of attention. Concepts like wave-particle duality may not be as well known, but they have fundamentally changed our understanding of the nature of light and matter. In this video, we will explore 7 of Einstein's most influential theories, unraveling the genius behind his discoveries. By the end, you'll have a comprehensive understanding of what Einstein believed to be true, how he arrived at these groundbreaking conclusions, and how subsequent generations have built upon or challenged his ideas since his passing. Our goal is to break down these complex theories into easily digestible insights, offering a window into the mind of a genius who dared to question the very fabric of reality. So, without further ado, let's begin our journey with one of his most famous and far-reaching theories, the theory of relativity. Let's dive into the profound world of Einstein's general theory of relativity, a theory that fundamentally reshaped our understanding of gravity, space, and time. Published in 1915, this groundbreaking theory provided a new framework for describing the force of gravity, moving beyond the classical views of Newtonian mechanics. Instead of viewing gravity as a simple attraction between two masses, Einstein proposed that gravity is a geometric property of space and time itself, a concept that continues to influence our understanding of the universe today. To appreciate the genius of Einstein's general theory of relativity, it helps to first consider the world before Einstein. In the classical Newtonian view, gravity was seen as a force acting at a distance, pulling objects toward one another. According to Newton's law of universal gravitation, this force was proportional to the mass of the objects and inversely proportional to the square of the distance between them. While this description was remarkably successful in explaining the motion of planets and the behavior of falling objects, it did not account for all phenomena. For example, the orbit of Mercury showed deviations that could not be explained by Newtonian physics alone. Einstein's revolutionary idea was to view gravity not as a force, but as a curvature of space-time caused by mass. In this new model, massive objects like stars and planets warp the fabric of space-time around them, much like how a heavy ball placed on a rubber sheet causes the sheet to stretch and curve. Smaller objects like planets or light rays move along paths determined by this curvature. In this sense, objects are not pulled by gravity, but follow the natural contours of the space-time landscape, a concept that radically altered our understanding of motion and gravitation. At the heart of this theory are the Einstein field equations, a set of 10 interrelated differential equations that describe how matter and energy in the universe influence the curvature of space-time. These equations are complex and often difficult to solve, but they provide a precise mathematical framework for understanding the dynamics of the cosmos. One of the key predictions of these equations is the existence of black holes, regions of space where the gravitational pull is so strong that not even light can escape. One of the most fascinating aspects of general relativity is how it redefines our understanding of time. In Newtonian physics, time is absolute and ticks at the same rate for everyone, everywhere. However, Einstein showed that time is relative and can vary depending on the strength of a gravitational field. This phenomenon, known as gravitational time dilation, means that time passes more slowly in stronger gravitational fields. For example, a clock on the surface of the Earth will tick slightly slower than a clock positioned far from any massive body in space. This effect, although minuscule in everyday life, has significant implications for understanding the universe and is even accounted for in the operation of GPS satellites. One of the early confirmations of general relativity came from the study of Mercury's orbit. Observations showed that the planet's orbit slowly shifts over time, a phenomenon known as the precession of the perihelion. Newtonian physics could not fully explain this anomaly, but Einstein's equations predicted precisely the observed precession, providing one of the first pieces of evidence supporting his theory. This success not only validated general relativity, but also marked a turning point in our understanding of gravity. General relativity also predicts the bending of light by gravity, known as gravitational lensing. This occurs when light from a distant star or galaxy passes near a massive object, like a galaxy cluster, and is bent due to the curvature of space-time. This bending can create multiple images of the same astronomical object, as well as rings or arcs, and has become an essential tool in modern astrophysics. Gravitational lensing allows astronomers to study the distribution of dark matter, which does not emit light and can only be detected through its gravitational effects. Another remarkable prediction of general relativity is the existence of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. Einstein first predicted these waves in 1916, but it took nearly a century for technology to catch up and confirm their existence. In 2015, the LIGO Observatory made the first direct detection of gravitational waves generated by the merger of two black holes over 1 billion light-years away. This discovery opened a new era in astronomy, allowing scientists to observe and study cosmic events in an entirely new way. General relativity also plays a crucial role in our understanding of the universe's large-scale structure. It provides the foundation for the theory of an expanding universe, which was first proposed by Alexander Friedmann and later supported by Edwin Hubble's observations. This expansion is described by the Friedmann equations, derived from Einstein's field equations, which have led to the development of the Big Bang theory and the discovery of the cosmic microwave background radiation. These discoveries have transformed cosmology, providing a coherent narrative of the universe's evolution from its hot and dense beginnings to its current state. Despite its successes, general relativity is not without its challenges. One of the biggest issues is reconciling it with quantum mechanics, the theory that describes the behavior of particles at the smallest scales. While general relativity excels at describing large-scale phenomena, like the motion of planets and the dynamics of galaxies, quantum mechanics governs the subatomic realm, where particles exhibit wave-particle duality and uncertainty. The quest for a theory of quantum gravity, which would unite these two pillars of modern physics, remains one of the most significant challenges in theoretical physics. General relativity's elegance and explanatory power have earned it a reputation as one of the most beautiful theories in physics. Its ability to describe the universe's vast complexities with a simple yet profound framework speaks to the depth of Einstein's genius. It challenges our intuitions about space and time, inviting us to see the universe not as a static backdrop, but as a dynamic and interconnected web where mass and energy shape the very fabric of reality. In everyday life, the effects of general relativity are subtle yet profound. They play a crucial role in the functioning of GPS systems, which must account for time dilation effects to provide accurate location data. Without these corrections, the synchronization of satellite clocks with those on Earth would drift, leading to significant errors in positioning. As we continue to explore the universe, general relativity remains an indispensable tool in our quest to understand the cosmos. It guides our studies of exotic objects like neutron stars and black holes, and it helps us map the distribution of matter in the universe. Its predictions have been confirmed through countless observations and experiments, from the bending of starlight during a solar eclipse to the detection of gravitational waves from merging black holes. Einstein's general theory of relativity stands as a testament to the power of human curiosity and the relentless pursuit of knowledge. It challenges us to look beyond the surface and explore the underlying principles that govern our universe. As we delve deeper into its mysteries, we continue to uncover new insights that enrich our understanding of the cosmos and our place within it. This theory not only reshapes our view of gravity, but also inspires us to seek answers to the most profound questions about the nature of reality itself. In 1905, Albert Einstein revolutionized the world of physics with his quantum theory of light, which introduced the concept that light is made up of tiny packets of energy called photons. This theory was a radical departure from the prevailing wave theory of light, which viewed light as a continuous electromagnetic wave. By proposing that light exhibited both particle-like and wave-like properties, Einstein laid the groundwork for the development of quantum mechanics and fundamentally changed our understanding of the nature of light. Before Einstein's groundbreaking work, the scientific community widely accepted the wave theory of light. This theory was strongly supported by the work of James Clerk Maxwell, who had demonstrated that light was a form of electromagnetic radiation, traveling in waves through space. However, there were certain phenomena that the wave theory could not adequately explain. One such phenomenon was the photoelectric effect, a curious observation where light shining on certain metals would cause them to emit electrons, a process that classical wave theory could not satisfactorily describe. The photoelectric effect had first been observed by Heinrich Hertz in 1887, while he was experimenting with electromagnetic waves. Hertz noticed that ultraviolet light caused sparks to jump more easily across a gap in a metal circuit. This observation was intriguing, but it wasn't immediately clear why the effect occurred. Further experimentation by Philippe Lenard showed that the energy of the emitted electrons was independent of the intensity of the light, but rather depended on the light's frequency. This was puzzling because, according to classical physics, a more intense light source should impart more energy to the electrons. Einstein's quantum theory of light provided a brilliant explanation for this anomaly. He proposed that light is composed of discrete packets of energy, or photons, each with an energy proportional to the frequency of the light. This idea was based on the work of Max Planck, who had previously introduced the concept of quantization to explain blackbody radiation. Planck's constant, a fundamental physical constant, relates the energy of a photon to its frequency through the equation E equals h times F, where E is energy, h is Planck's constant, and F is the frequency. Einstein realized that if light were made up of photons, then only photons with sufficient energy, determined by their frequency, could liberate electrons from the surface of a metal. This insight explained why the photoelectric effect depended on the frequency rather than the intensity of light. A higher frequency light source would have more energetic photons, capable of knocking electrons loose from the metal surface, while a lower frequency light, no matter how intense, would not have enough energy to do so. This particle-like behavior of light was a revolutionary concept because it challenged the traditional wave theory and introduced the idea of wave-particle duality. Light, according to Einstein, could behave as both a wave and a particle, depending on the circumstances. This dual nature of light became a cornerstone of quantum mechanics and profoundly influenced the development of modern physics. The quantum theory of light not only explained the photoelectric effect, but also had far-reaching implications for the understanding of electromagnetic radiation. It suggested that all forms of electromagnetic radiation, including visible light, ultraviolet light, X-rays, and gamma rays, could be described in terms of photons. This idea paved the way for new technologies, such as the development of photovoltaic cells, which convert light into electricity by exploiting the photoelectric effect. The concept of photons also revolutionized the field of optics and led to the development of quantum optics, a branch of physics that explores the behavior of light and its interactions with matter at the quantum level. Quantum optics has given rise to numerous technological advances, including lasers, which rely on the stimulated emission of photons, and quantum computing, which seeks to harness the principles of quantum mechanics to perform computations far more efficiently than classical computers. Einstein's quantum theory of light also had significant philosophical implications. It challenged the deterministic worldview of classical physics by introducing elements of uncertainty and probability into the fundamental description of nature. The notion that light could exist in discrete packets and that its behavior could be probabilistic rather than deterministic was a radical departure from the classical understanding of the universe. Despite its revolutionary impact, the quantum theory of light was not immediately accepted by all scientists. Some physicists were uncomfortable with the idea of light as a particle, as it contradicted the wave-based descriptions that had been so successful in explaining phenomena like interference and diffraction. Nevertheless, over time, the evidence supporting the quantum nature of light became overwhelming, and Einstein's theory gained widespread acceptance. One of the most compelling pieces of evidence for the quantum theory of light came from experiments conducted by Arthur Compton in the 1920s. Compton studied the scattering of X-rays by electrons and found that the X-rays behaved as particles, transferring energy and momentum to the electrons in discrete amounts. This phenomenon, known as the Compton effect, provided strong support for the idea that light could indeed behave as a particle. The quantum theory of light also helped to resolve the so-called ultraviolet catastrophe, a problem that had plagued classical physics. According to classical theories, a black body should emit an infinite amount of ultraviolet radiation, a result that was clearly inconsistent with observations. By treating light as quantized, Planck and Einstein were able to accurately describe black body radiation and eliminate this theoretical inconsistency. As the understanding of the quantum nature of light evolved, it became clear that other particles, such as electrons and atoms, also exhibited wave-particle duality. This realization led to the development of quantum mechanics, a theoretical framework that describes the behavior of particles at the atomic and subatomic levels. Quantum mechanics introduced a new way of thinking about the physical world, emphasizing the probabilistic nature of particles and their interactions. Einstein's contributions to the quantum theory of light were instrumental in shaping the field of quantum mechanics, even though he himself had reservations about some of its implications. Throughout his life, Einstein remained skeptical of the indeterministic nature of quantum mechanics, famously stating that God does not play dice with the universe. Despite his reservations, Einstein's work on the quantum theory of light laid the groundwork for a century of scientific discovery and innovation. The quantum theory of light continues to influence scientific research and technological development. In recent years, advances in quantum optics and photonics have led to the creation of new technologies, such as quantum cryptography, which uses the principles of quantum mechanics to create secure communication channels, and quantum teleportation, which allows for the transfer of quantum information between distant locations. The impact of Einstein's quantum theory of light is also evident in the field of astronomy, where it has enabled the study of cosmic phenomena through the detection of photons across the electromagnetic spectrum. From the detection of cosmic microwave background radiation, which provides insights into the early universe, to the observation of distant galaxies and black holes, photons play a crucial role in expanding our understanding of the cosmos. In medicine, the principles of quantum theory and the understanding of photons have contributed to the development of imaging technologies such as positron emission tomography and magnetic resonance imaging, which rely on the interactions between photons and matter to create detailed images of the human body. Einstein's quantum theory of light has also influenced the study of fundamental particles and forces, contributing to the development of the Standard Model of particle physics. The model describes the behavior of elementary particles and their interactions through the exchange of force-carrying particles, many of which are understood in terms of quantum field theory. The exploration of light's quantum nature has led to the development of cutting-edge research in areas such as quantum entanglement and quantum coherence, which hold promise for advancing our understanding of complex systems and may pave the way for future technologies like quantum networks and quantum sensors. In summary, Albert Einstein's quantum theory of light was a transformative idea that reshaped our understanding of the nature of light and laid the foundation for the development of quantum mechanics. By introducing the concept of photons and wave-particle duality, Einstein challenged the classical view of light and opened the door to a new era of scientific discovery. His work not only explained phenomena like the photoelectric effect, but also provided a framework for understanding the quantum behavior of matter and energy. Today, the quantum theory of light remains a central pillar of modern physics, influencing a wide range of scientific disciplines and technological advancements. From the study of fundamental particles to the development of innovative technologies, Einstein's insights continue to illuminate our understanding of the universe and inspire new generations of scientists to explore the mysteries of the quantum world. In 1905, Albert Einstein published his groundbreaking paper on the special theory of relativity, forever changing the landscape of physics. This theory addressed the relationship between space and time, presenting a new framework that resolved inconsistencies in the laws of motion and electromagnetism, particularly with Maxwell's equations. Unlike Newtonian mechanics, which had dominated physics for centuries, Einstein's special relativity introduced concepts that were both revolutionary and counterintuitive, challenging our understanding of the universe at its core. The special theory of relativity applies to what Einstein described as special cases involving high speeds and energies without the complicating effects of gravity. This theory proposed that the laws of physics are the same for all observers in uniform motion relative to each other, which means that no matter how fast they are moving, the speed of light in a vacuum remains constant at approximately 300,000 kilometers per second. This was a radical departure from classical physics, which assumed that speeds and distances were absolute and the same for all observers. The key to understanding the special theory of relativity is recognizing that time and space are interconnected, forming a four-dimensional continuum known as space-time. In this framework, the passage of time is not uniform but can vary depending on an observer's relative motion. This concept is known as time dilation, where time effectively slows down for an object in motion compared to one at rest. A famous thought experiment illustrates this idea. Imagine a train traveling close to the speed of light. If a passenger on the train observes two lightning strikes hitting both ends of the train simultaneously, an observer standing on the platform outside the train might see one lightning strike before the other. For the stationary observer, the light from the rear of the train takes longer to catch up because the train is moving away from the strike. Both observers are correct in their observations, highlighting that simultaneity is not an absolute concept, but depends on the observer's frame of reference. This notion of relative time led to one of the most famous equations in physics, E equals mc squared, where E is energy, m is mass, and c is the speed of light. This equation implies that mass and energy are interchangeable, revealing that a small amount of mass can be converted into a tremendous amount of energy. This insight has profound implications, not only for theoretical physics, but also for practical applications like nuclear energy, where small amounts of matter are transformed into large amounts of energy. Before Einstein, Isaac Newton's laws of motion had provided a comprehensive framework for understanding the physical world. Newton's first law, the law of inertia, stated that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. His second law related force to mass and acceleration, while his third law asserted that every action has an equal and opposite reaction. These laws worked well for everyday phenomena, but encountered challenges when applied to light and high-speed scenarios. One major challenge was explaining the behavior of light within Newtonian physics. Scientists in the 19th century had posited the existence of a medium called the luminiferous ether, through which light waves were thought to propagate. However, the ether's existence was purely hypothetical, as it was never detected in experiments. In 1887, the famous Michelson-Morley experiment demonstrated that the speed of light was constant regardless of Earth's motion through the ether, leading to the conclusion that such an ether did not exist. This unexpected result called for a new theoretical approach, paving the way for Einstein's work. Einstein's special theory of relativity addressed the limitations of classical mechanics by discarding the notion of absolute space and time. It posited that the laws of physics should be consistent for all observers, regardless of their motion. This required rethinking fundamental concepts like simultaneity and the relationship between time and space. One of the most profound implications of special relativity is the concept of mass-energy equivalence. embodied in the equation E equals mc squared. This principle underlies many technological advances and scientific discoveries, including the development of nuclear power and our understanding of the sun's energy production through nuclear fusion. The equation also implies that as an object's speed approaches the speed of light, its mass effectively becomes infinite, requiring an infinite amount of energy to accelerate further. This establishes a cosmic speed limit, making faster-than-light travel impossible according to the theory. Special relativity also introduced the concept of length contraction, which states that objects moving at relativistic speeds appear shorter in the direction of motion to a stationary observer. This phenomenon, like time dilation, results from the relativity of simultaneity and the intertwined nature of space and time. These effects are not noticeable at everyday speeds, but become significant as velocities approach the speed of light. The practical implications of special relativity extend beyond theoretical physics. For instance, the theory plays a crucial role in the functionality of the global positioning system. GPS satellites orbiting the Earth experience both gravitational time dilation, as described by general relativity, and the effects of their high velocity, as predicted by special relativity. The onboard atomic clocks must account for these relativistic effects to provide accurate positioning data to receivers on Earth. Without these adjustments, the system would quickly become inaccurate, highlighting the theory's importance in modern technology. Special relativity also influences our understanding of cosmology and the universe's structure. It provides a framework for interpreting phenomena such as cosmic rays, which travel at speeds approaching the speed of light, and helps scientists study the behavior of particles in high-energy accelerators. The theory's insights into the behavior of light and energy contribute to our understanding of the early universe and the formation of galaxies and stars. While special relativity addresses scenarios involving high speeds and energies, Einstein's later work, the general theory of relativity, expanded these ideas to include gravity. General relativity describes how massive objects like planets and stars curve space-time, causing the gravitational effects we observe. Unlike special relativity, which applies to inertial frames of reference, general relativity considers the effects of acceleration and gravity, providing a more comprehensive picture of the universe. Despite the differences between special and general relativity, both theories are united by their reliance on the constancy of the speed of light and the relativity of motion. They underscore the idea that space and time are not separate entities, but are interconnected dimensions of space-time. This profound shift in perspective has had far-reaching consequences for physics, prompting new questions about the fundamental nature of reality. Einstein's special theory of relativity has also inspired science fiction and philosophical exploration. The concept of time dilation and the possibility of traveling vast distances through space have fueled imaginative scenarios in literature and film. These stories often explore the implications of relativistic travel, such as the effects on aging and communication across light years, illustrating the theory's enduring impact on popular culture. In the realm of particle physics, special relativity has been instrumental in understanding the behavior of subatomic particles and their interactions. The theory's principles are fundamental to the operation of particle accelerators, which propel particles to near light speeds to study their properties and interactions. This research has led to discoveries that deepen our understanding of the universe's building blocks, contributing to the development of the standard model of particle physics. Special relativity also plays a crucial role in astrophysics, where it helps explain phenomena such as the bending of light around massive objects and the formation of black holes. The theory's predictions about the behavior of light and energy have been confirmed through astronomical observations, further solidifying its status as a cornerstone of modern physics. While special relativity and quantum mechanics initially seemed at odds, efforts to reconcile them have led to the development of relativistic quantum mechanics and quantum field theory. These frameworks attempt to bridge the gap between the macroscopic world of relativity and the microscopic realm of quantum physics, providing a more unified understanding of the universe. In conclusion, Albert Einstein's special theory of relativity fundamentally transformed our understanding of the universe. By challenging the classical notions of absolute space and time, Einstein introduced a new framework that accounts for the relativistic effects experienced at high speeds. The theory's insights into the relationship between mass, energy, and the speed of light have had profound implications for science, technology, and philosophy, shaping our understanding of the cosmos and inspiring generations of scientists and thinkers. The phenomenon of Brownian motion was first observed by the Scottish botanist Robert Brown in the year 1827. Brown noticed that tiny particles suspended in a liquid like pollen grains in water exhibited a continuous erratic motion. Initially, this movement puzzled scientists who could not determine the cause of the seemingly random oscillations. While the phenomenon was fascinating, it was Albert Einstein's groundbreaking work in the early 20th century that provided a comprehensive theoretical explanation for Brownian motion, thereby contributing significantly to the validation of atomic theory. Einstein's journey into Brownian motion began as part of his broader efforts to understand the microscopic world and validate the existence of atoms and molecules. By the early 1900s, the kinetic theory of gases, developed by physicists like James Clerk Maxwell, Ludwig Boltzmann, and Rudolf Clausius, had proposed that molecules in a gas are constantly in motion. This theory explained various heat phenomena and suggested that temperature is proportional to the average kinetic energy of the molecules. However, direct evidence of atoms remained elusive. In the year 1905, Einstein published a paper that would revolutionize our understanding of microscopic particles. In it, he proposed a quantitative theory of Brownian motion. He demonstrated that the random motion of particles suspended in a fluid could be attributed to the incessant bombardment by the molecules of the fluid. These molecules, though invisible to the naked eye, were in constant, rapid motion due to thermal energy. When they collided with suspended particles, they imparted momentum, causing the particles to jiggle and move in unpredictable ways. This insight provided the first tangible evidence of the kinetic theory of gases and supported the reality of atoms. Einstein's approach to Brownian motion was rigorous and mathematical. He employed statistical mechanics to predict the behavior of microscopic particles under the influence of molecular collisions. According to Einstein, a particle suspended in a liquid would experience a random difference in molecular pressure on its opposite sides, causing it to wobble and move back and forth. Over time, the cumulative effect of these random collisions would cause the particle to drift from its original position. One of Einstein's key contributions was the derivation of an equation that related the diffusion coefficient of a particle to its average displacement over time. He showed that the mean square displacement of a particle is directly proportional to time and inversely proportional to the viscosity of the fluid. This equation, now known as the Einstein-Smoluchowski relation, provided a framework for calculating the expected motion of particles in a fluid based on their size and the fluid's properties. It laid the foundation for understanding diffusion as a macroscopic manifestation of microscopic Brownian motion. Einstein's work on Brownian motion had far-reaching implications. It offered a method to determine the size of atoms and molecules, bridging the gap between theoretical predictions and experimental observations. By observing the motion of colloidal particles and applying Einstein's equations, scientists could infer the presence and size of the invisible molecules causing the motion. This provided a tangible way to measure Avogadro's number, the number of entities in a mole of a substance, thereby offering strong support for the atomic theory. The significance of Einstein's theory was not immediately recognized. However, its implications soon became apparent as scientists began to conduct experiments to verify his predictions. One of the most notable experiments was conducted by the French physicist Jean-Baptiste Perrin between the years 1905 and 1911. Perrin meticulously measured the movement of small particles suspended in a liquid and compared his observations with Einstein's theoretical predictions. His results were in excellent agreement, providing compelling evidence for the existence of atoms and molecules as physical entities. Perrin's work was instrumental in establishing the physical theory of Brownian motion and cemented the acceptance of atomic theory within the scientific community. For his contributions, Perrin was awarded the Nobel Prize in Physics in the year 1926. This marked a turning point in the history of science, as it ended the skepticism surrounding the existence of atoms and provided a concrete foundation for the development of modern chemistry and physics. Einstein's theory of Brownian motion also had profound implications for various fields beyond physics. It provided insights into processes such as diffusion, where substances spread from regions of high concentration to regions of lower concentration. By simulating the motion of Brownian particles, scientists could study diffusion phenomena in diverse contexts, from the spread of pollutants in the atmosphere to the movement of nutrients and ions in biological systems. Moreover, Brownian motion found applications in the burgeoning field of financial mathematics. In the early 20th century, French mathematician Louis Bachelier independently explored Brownian motion in the context of stock prices, laying the groundwork for the mathematical modeling of financial markets. His work, though initially overlooked, eventually became a cornerstone of modern finance, influencing the development of models like the Black-Scholes equation for option pricing. In addition to its theoretical contributions, the study of Brownian motion has practical applications in technology and industry. The phenomenon is utilized in techniques such as dynamic light scattering, which is used to measure the size of nanoparticles and macromolecules in solutions. This technique is widely employed in fields ranging from pharmaceuticals to materials science, where understanding the size distribution of particles is crucial for product development and quality control. The advent of the ultramicroscope in the early 20th century further advanced the study of Brownian motion. This powerful tool enabled scientists to visualize colloidal particles with greater precision, facilitating quantitative studies of their motion. Researchers could now measure the activity of these particles and verify the predictions of Einstein's theory with greater accuracy, reinforcing the connection between theory and experiment. Einstein's work on Brownian motion was a testament to his remarkable ability to bridge theoretical physics with experimental observations. It showcased his deep understanding of statistical mechanics and his skill in deriving meaningful insights from complex phenomena. This work, along with his other contributions, cemented his legacy as one of the most influential scientists in history. Despite the passage of over a century since Einstein's publication, Brownian motion continues to be a topic of active research. Scientists are exploring new dimensions of this phenomenon, investigating its implications in nanoscale systems, biological processes, and complex fluids. Advances in experimental techniques such as single particle tracking and super-resolution microscopy are providing new insights into the behavior of particles in diverse environments. In recent years, researchers have also explored the connections between Brownian motion and other areas of physics, such as quantum mechanics and thermodynamics. The study of quantum Brownian motion, for example, seeks to understand how quantum effects influence the random motion of particles at very small scales. This line of inquiry has implications for quantum information processing and the development of quantum technologies. Furthermore, the principles of Brownian motion are being applied to the design of novel materials and devices. Engineers and scientists are leveraging the random motion of particles to create systems that harness energy from fluctuations, such as microscopic engines and sensors. These innovations hold promise for a wide range of applications, from energy harvesting to environmental monitoring. In conclusion, Albert Einstein's exploration of Brownian motion was a pivotal moment in the history of science. His theoretical framework provided a compelling explanation for the erratic movement of particles in fluids and offered empirical support for the existence of atoms and molecules. This work not only resolved long-standing questions about the nature of matter, but also laid the foundation for advancements in diverse fields, from chemistry to finance. As we continue to unravel the mysteries of the microscopic world, the legacy of Einstein's insights into Brownian motion remains a guiding light for scientific exploration and discovery. The photoelectric effect is one of the cornerstone concepts in modern physics, playing a crucial role in the development of quantum mechanics and our understanding of the nature of light. The phenomenon was explained in a groundbreaking way by Albert Einstein, who introduced the revolutionary idea of photons, or quanta of light, to describe how light interacts with matter. The photoelectric effect describes the emission of electrons from a material, typically a metal, when it is exposed to electromagnetic radiation, such as ultraviolet light. These emitted electrons are known as photoelectrons. The study of this effect has provided significant insights into the properties of atoms, molecules, and solids, and it has found practical applications in various electronic devices designed for light detection and precision timing. Before Einstein's contribution, the classical wave theory of light struggled to explain the photoelectric effect. Classical electromagnetism predicted that light waves would transfer energy continuously to electrons, causing them to be emitted when they accumulated enough energy. According to this theory, the kinetic energy of the emitted electrons should depend on the intensity of the light, with dim light resulting in a delayed emission. However, experimental results contradicted these predictions. The experiments showed that electrons are emitted only when the light exceeds a certain frequency, regardless of the intensity or duration of exposure. This suggested that light does not behave like a continuous wave, but rather as discrete packets of energy. These energy packets are what Einstein called photons. Each photon carries a specific energy proportional to the frequency of the light. Einstein's theory of the photoelectric effect proposed that when electromagnetic radiation, such as light, strikes a metal surface, it transfers energy to electrons in the material. If the photon energy is sufficient, the electron absorbs the energy and is ejected from the material. The process is akin to knocking an electron loose with a tiny hammer made of light. The groundbreaking aspect of Einstein's theory was the realization that the energy of the emitted photoelectrons depends only on the frequency of the incoming light, not its intensity. This explained why low-frequency light, even at high intensity, could not produce photoelectrons, while high-frequency light, even at low intensity, could. It was a clear indication that light behaves as both a wave and a particle, embodying the concept of wave-particle duality. Einstein's insights into the photoelectric effect challenged the classical understanding of light and paved the way for the development of quantum mechanics. His work demonstrated that light must be thought of as consisting of discrete energy packets rather than continuous waves. This was a radical departure from the prevailing theories of the time and contributed to the shift towards a new quantum view of the physical world. The photoelectric effect has practical applications in technologies such as solar cells. In these devices, light striking a semiconductor material causes the release of electrons, generating an electric current. This is the basis for converting sunlight into electricity, a process that powers a growing portion of our modern world. In Einstein's model, when light strikes the surface of a metal, its photons are absorbed by the electrons within the material. If the energy of a photon exceeds the electron's binding energy, the electron is ejected from the material as a photoelectron. The remaining energy of the photon is transferred to the electron as kinetic energy, allowing it to escape the material's surface. An important implication of Einstein's theory is the existence of a threshold frequency, below which no photoelectrons are emitted, regardless of the light's intensity. This threshold frequency corresponds to the minimum photon energy required to overcome the binding energy of the electrons in the material. Above this frequency, the kinetic energy of the emitted electrons increases linearly with the frequency of the incoming light. This relationship between photon energy and electron emission was confirmed experimentally by Robert Millikan in 1914, who conducted precise measurements of the photoelectric effect. Despite initially being skeptical of Einstein's photon theory, Millikan's experiments supported Einstein's predictions. His work earned Millikan the Nobel Prize in Physics in the year 1923, and it provided strong evidence for the quantized nature of light. Einstein's explanation of the photoelectric effect was a key factor in his award of the Nobel Prize in Physics in the year 1921. His insights laid the foundation for the quantum theory of light and had profound implications for the understanding of atomic and molecular processes. The study of the photoelectric effect also contributed to the development of the concept of wave-particle duality. This idea, which emerged from the work of Einstein and others, describes how light and other quantum particles can exhibit both wave-like and particle-like behavior. The dual nature of light challenged traditional notions of physics and inspired new ways of thinking about the fundamental nature of the universe. In addition to its theoretical significance, the photoelectric effect has practical applications in various fields. In addition to its role in solar cells, the effect is utilized in devices such as photodetectors, which convert light into an electrical signal for use in cameras and other imaging systems. These devices are critical components in modern technology, enabling everything from digital photography to advanced scientific instruments. The photoelectric effect also plays a role in the field of spectroscopy, where it is used to study the properties of materials. By analyzing the energy and distribution of photoelectrons emitted from a material's surface, scientists can gain insights into its electronic structure and chemical composition. This information is invaluable for understanding the behavior of complex materials and developing new technologies. The photoelectric effect remains an active area of research, with scientists continuing to explore its implications and applications. Advances in technology have enabled the study of the effect in new contexts, such as nanoscale materials and quantum systems. These studies are shedding light on the fundamental interactions between light and matter, with potential implications for fields ranging from materials science to quantum computing. In conclusion, the photoelectric effect is a landmark discovery that revolutionized our understanding of light and matter. Albert Einstein's explanation of the effect, which introduced the concept of photons, was a pivotal moment in the development of quantum mechanics. The photoelectric effect not only challenged classical theories of physics, but also opened up new avenues for scientific exploration and technological innovation. Its legacy continues to shape our understanding of the quantum world and inspire new generations of scientists and engineers. The concept of wave-particle duality is one of the most profound ideas in quantum mechanics, revolutionizing our understanding of the nature of light and matter. At the heart of this concept is the realization that quantum entities, such as photons and electrons, can exhibit both wave-like and particle-like properties depending on the circumstances. This duality challenges the classical view of physics, where waves and particles were considered distinct entities with separate behaviors. Albert Einstein's contributions to this field were pivotal in establishing wave-particle duality as a fundamental principle of quantum mechanics. Einstein's early work in quantum theory focused on light, which had been traditionally described as a wave phenomenon. During the 19th century, experiments such as Thomas Young's double-slit experiment had demonstrated the wave nature of light through interference patterns. However, Einstein's investigation into the photoelectric effect in 1905 revealed the particle-like behavior of light, where light was found to consist of discrete energy packets, later called photons. This discovery suggested that light could behave both as a wave and as a particle, depending on the experimental setup. Einstein's insight into wave-particle duality extended beyond light to include matter as well. He proposed that the duality observed in light could also apply to particles of matter, such as electrons. This idea was further developed by physicist Louis de Broglie, who introduced the concept of matter waves in the early 1920s. De Broglie suggested that particles like electrons could exhibit wave-like properties, with wavelengths determined by their momentum. This proposal laid the groundwork for the development of wave mechanics, an essential part of quantum mechanics. Wave-particle duality is best illustrated through experiments that demonstrate both wave-like and particle-like behavior. One of the most famous experiments highlighting this duality is the electron double-slit experiment. When electrons are fired at a barrier with two slits, they produce an interference pattern on a screen behind the barrier, similar to the pattern observed with light waves. However, when detectors are placed at the slits to determine which slit the electrons pass through, the interference pattern disappears and the electrons behave like particles. This experiment vividly demonstrates that electrons, like light, can exhibit both wave and particle characteristics depending on the measurement. Einstein's contributions to wave-particle duality were not limited to his theoretical insights. He was instrumental in shaping the development of quantum mechanics by advocating for a new understanding of light and matter. His work challenged classical physics and inspired a generation of scientists to explore the fundamental nature of the universe. Einstein's influence on quantum mechanics extends beyond wave-particle duality. His insistence on the dual nature of light and matter laid the groundwork for the development of key quantum concepts, such as the uncertainty principle and quantum superposition. These ideas form the basis of modern quantum mechanics, a framework that has transformed our understanding of the physical world. The implications of wave-particle duality are profound, affecting not only our understanding of the natural world, but also the development of new technologies. The dual nature of light and matter is harnessed in various applications, from electron microscopes that use the wave properties of electrons to probe the structure of materials at the atomic level, to quantum computers that exploit the principles of superposition and entanglement to perform calculations beyond the reach of classical computers. In addition to its practical applications, wave-particle duality has philosophical implications, challenging our understanding of reality and the nature of knowledge. The duality suggests that the properties of quantum entities are not inherent, but depend on the observer and the experimental conditions. This realization has led to debates about the nature of reality and the role of the observer in the physical world. Einstein's contributions to wave-particle duality are part of his broader legacy in physics. His relentless questioning of established theories and his willingness to embrace new ideas set a standard for scientific inquiry. He recognized that the complexity of the universe could not be captured by simple models, and that a deeper understanding required new ways of thinking about space, time, and matter. Einstein's famous quote, "We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do," captures the essence of wave-particle duality. This duality, while challenging to reconcile with classical notions of physics, provides a more complete picture of the quantum world and reflects the intricate nature of the universe. In conclusion, wave-particle duality is a cornerstone of quantum mechanics, providing a framework for understanding the dual nature of light and matter. Albert Einstein's contributions to this concept were instrumental in shaping the development of quantum theory and challenging classical physics. His work laid the foundation for a new understanding of the universe, inspiring generations of scientists to explore the mysteries of the quantum world. The legacy of wave-particle duality continues to influence scientific inquiry and technological innovation, reflecting the enduring impact of Einstein's insights on modern physics. The concept of an Einstein-Rosen bridge, more popularly known as a wormhole, is one of the most captivating ideas in theoretical physics. Introduced by Albert Einstein and his colleague Nathan Rosen in the year 1935, this theory explores the possibility of shortcuts through space-time, connecting two separate points in the universe. The Einstein-Rosen bridge emerges from the mathematics of Einstein's general theory of relativity. It is a solution to the Einstein field equations, which describe the fundamental interaction of gravitation as a result of space-time being curved by matter and energy. These bridges, or wormholes, are a theoretical passage through space-time that could create shortcuts for long journeys across the universe. Imagine bending a piece of paper with two pencil marks drawn on it, representing 2 points in space. If you fold the paper and punch a hole through the marks, the hole represents a wormhole, connecting the 2 separate points with a direct path. The Einstein-Rosen bridge is visualized as a tunnel-like structure with 2 openings, each located at different points in space-time. Einstein and Rosen discovered that their theoretical wormholes could exist within the framework of a Schwarzschild black hole, a solution to the field equations that describes a black hole with no charge and no rotation. Within this structure, the wormhole connects the interior of a black hole to an exterior white hole, an area theorized to allow matter and light to escape. This configuration implies that the wormhole forms a bridge between two different regions of space-time. These regions could be in the same universe or potentially in entirely different universes. However, this theoretical bridge is not stable. It pinches off too quickly for anything to travel through it. One of the major challenges with the concept of the Einstein-Rosen bridge is its stability. In the 1960s, physicists John Archibald Wheeler and Robert W. Fuller demonstrated that such a bridge is inherently unstable. If a wormhole connects two parts of the same universe, it collapses almost instantaneously, preventing any matter or information from passing through. This instability arises because the wormhole requires exotic matter with negative energy density, to keep it open. Exotic matter is purely theoretical and has not been observed in nature. Without it, the bridge collapses, closing the pathway between its two ends. Despite these challenges, the idea of a traversable wormhole has continued to inspire physicists and science fiction writers alike. The notion of using exotic matter to hold the throat of a wormhole open remains a popular subject in theoretical explorations of space-time. The idea of wormholes has captured the imagination of both scientists and the public. They offer a tantalizing possibility of faster-than-light travel and time travel, allowing for exploration of the universe in ways that defy our current understanding of physics. Wormholes have become a staple in science fiction, featuring in books, movies, and television shows as a means of interstellar travel and adventure. In theoretical physics, the study of wormholes continues to provide insights into the nature of the universe. They challenge our understanding of space-time, suggesting that the universe may be far more interconnected than we perceive. Wormholes also offer potential explanations for phenomena such as black holes and quantum entanglement, deepening our exploration of the cosmos. The Einstein-Rosen bridge remains one of the most fascinating and enigmatic concepts in physics. While still purely theoretical, it challenges our perceptions of reality and fuels our curiosity about the universe's mysteries. The quest to understand and potentially harness the power of wormholes continues to inspire physicists, encouraging them to push the boundaries of what we know about the nature of space and time. Albert Einstein once described the inclusion of the cosmological constant in his equations of general relativity as the biggest blunder of his life. Yet this term, originally introduced to model a static universe, has found new relevance in modern cosmology. The cosmological constant, denoted by the Greek letter lambda, has become a pivotal factor in understanding the mysterious force known as dark energy, which drives the accelerated expansion of the universe. In 1917, Einstein added the cosmological constant to his general relativity equations to align with the prevailing belief at the time that the universe was static and unchanging. This addition allowed the equations to describe a universe that remained constant in size, counteracting the attractive force of gravity with a repulsive force. However, when observations by astronomers such as Edwin Hubble later revealed that the universe was expanding, Einstein quickly abandoned the cosmological constant, considering it an unnecessary complication and dubbing it his greatest mistake. Fast forward to the late 20th century, and the cosmological constant has experienced a renaissance in the scientific community. Observations of distant supernovae and the cosmic microwave background radiation have provided compelling evidence that the universe is not only expanding, but doing so at an accelerating rate. This unexpected acceleration suggests the presence of a mysterious form of energy, now known as dark energy, which permeates all of space and exerts a repulsive force that counteracts gravity. The cosmological constant is the simplest explanation for dark energy, proposing that it is an inherent property of space itself. Unlike ordinary matter and energy, dark energy does not dilute as the universe expands. Instead, it maintains a constant density, driving the accelerated expansion. The cosmological constant provides a mathematical framework for this behavior, suggesting that empty space possesses a built-in energy that influences the universe's dynamics. Recent studies have further bolstered the case for the cosmological constant as the leading explanation for dark energy. Physicists Christian Marinoni and Adeline Bouzy from the Université de Provence in France developed a novel method to test the dark energy model independently of previous approaches. Their technique involves observing pairs of distant galaxies to measure the curvature of space, providing insights into the geometry of the universe. The geometry of the universe is intrinsically linked to its contents, as Einstein's general relativity demonstrated that mass and energy bend space-time. Marinoni and Bouzy's research focused on determining the universe's shape, which can be flat like a plane, spherical like a globe, or hyperbolically curved like a saddle. Their findings align with previous studies that favor a flat universe model, supporting the cosmological constant as the best fit for dark energy. The researchers measured the redshift of light from galaxy pairs, which shifts toward the red end of the spectrum due to the Doppler effect as galaxies move away from us. By analyzing these redshift measurements, they plotted the orientation and position of the galaxies, revealing a universe that is predominantly flat. This result strengthens the cosmological constant model, as a flat universe is consistent with a cosmological constant value close to -1, the predicted value for dark energy. While the cosmological constant offers a compelling mathematical explanation for dark energy, it does not elucidate why this mysterious force exists. Understanding the nature of dark energy remains one of the most significant scientific challenges of our time. As Alan Hevans of the University of Edinburgh noted, determining the nature of dark energy and dark matter is considered the most important scientific question of the decade. The work of Marinoni and Bouzy represents a crucial step forward in this quest, providing a novel technique to test the cosmological model and enhancing our understanding of the universe's geometry. Despite its resurgence as a key component of modern cosmology, the cosmological constant remains a subject of debate and exploration. Some physicists propose alternative explanations for dark energy, such as modifications to the equations of general relativity. However, the cosmological constant remains the simplest and most widely accepted explanation, offering a straightforward way to incorporate dark energy into the framework of general relativity. Einstein's biggest blunder is now seen as a testament to his profound intuition and foresight. His willingness to explore new ideas, even those that initially seemed flawed, exemplifies the spirit of scientific inquiry. The cosmological constant, once considered a mistake, has become an essential element in our understanding of the universe's evolution and expansion. As scientists continue to study dark energy and its implications, the cosmological constant serves as a reminder of the complex and often surprising nature of the cosmos. It highlights the interconnectedness of theoretical insights and observational discoveries, demonstrating how science evolves through the interplay of ideas and evidence. Einstein's legacy, shaped by both triumphs and perceived blunders, continues to inspire and guide our exploration of the universe's mysteries. The renewed interest in the cosmological constant also underscores the importance of re-evaluating scientific ideas in light of new evidence. It encourages researchers to remain open to revisiting past assumptions and considering alternative perspectives, as our understanding of the universe is constantly evolving. Einstein's journey from regarding the cosmological constant as a mistake to its revival as a fundamental concept in cosmology illustrates the dynamic and iterative nature of scientific progress. In the context of the broader quest to understand the universe, the cosmological constant is a key piece of the puzzle. It represents an ongoing challenge to reconcile our theoretical models with the observational data, pushing the boundaries of our knowledge and prompting new questions about the nature of reality. As we continue to explore the cosmos, the lessons of Einstein's biggest blunder remind us that the path to understanding is often complex and non-linear, requiring both persistence and flexibility in the face of uncertainty. In conclusion, Einstein's cosmological constant, once dismissed as a blunder, has emerged as a vital component of modern cosmology, providing a framework for understanding dark energy and the accelerating expansion of the universe. The transformation from mistake to insight highlights the iterative nature of scientific discovery and the enduring impact of Einstein's work on our quest to unravel the mysteries of the cosmos. As we continue to investigate the nature of dark energy and the universe's geometry, the cosmological constant remains a central topic of study, guiding our efforts to comprehend the fundamental forces that shape our universe. Albert Einstein's contributions to science are nothing short of revolutionary, and his theories have left an indelible mark on our understanding of the universe. As we conclude our exploration of his profound insights, it's important to reflect on the broader implications of his work and how they continue to influence the world today. Einstein's theories challenged the classical views of physics, ushering in a new era of scientific thought. His ability to see beyond the limitations of existing theories and propose radical new ideas has had a lasting impact on the scientific community. Einstein's work not only transformed physics, but also inspired generations of scientists to think creatively and push the boundaries of human knowledge. The theory of relativity, both special and general, redefined our understanding of space and time. It introduced concepts such as time dilation, mass-energy equivalence, and the curvature of space-time, fundamentally changing how we perceive the universe. These ideas have had practical implications in fields ranging from cosmology to engineering, influencing everything from our understanding of black holes and gravitational waves to the functioning of GPS systems. Quantum theory of light, with its introduction of photons and wave-particle duality, laid the groundwork for the development of quantum mechanics. This theory challenged the classical notion of light as a continuous wave and introduced the idea that light can behave as both a wave and a particle. This duality has profound implications for our understanding of the nature of reality and has paved the way for advancements in quantum optics, quantum computing, and other cutting-edge technologies. Brownian motion, explained by Einstein, provided empirical evidence for the existence of atoms and molecules, supporting the atomic theory of matter. This work bridged the gap between theoretical predictions and experimental observations, laying the foundation for modern chemistry and physics. It also influenced fields such as finance and biology, where the principles of Brownian motion are applied to model complex systems. The photoelectric effect, which Einstein explained using the concept of photons, played a pivotal role in the development of quantum mechanics. This theory challenged classical views of light and helped establish the quantum nature of electromagnetic radiation. The photoelectric effect has practical applications in technologies such as solar cells and photodetectors, contributing to the advancement of renewable energy and imaging technologies. Wave-particle duality, a concept central to quantum mechanics, was profoundly influenced by Einstein's work. This duality challenges the classical separation of waves and particles, suggesting that quantum entities can exhibit both behaviors depending on the circumstances. The implications of wave-particle duality are far-reaching, influencing our understanding of fundamental particles and their interactions, and inspiring new approaches to quantum computing and information processing. The Einstein-Rosen bridge, or wormhole theory, explores the possibility of shortcuts through space-time, offering tantalizing prospects for faster-than-light travel and time travel. While still theoretical, the concept of wormholes challenges our perceptions of reality and fuels our curiosity about the universe's mysteries. The study of wormholes continues to inspire physicists and science fiction writers alike, encouraging exploration of the possibilities of space-time connectivity. As we reflect on Einstein's legacy, it becomes clear that his contributions extend beyond the realm of physics. His work has influenced a wide range of disciplines, from chemistry and engineering to philosophy and art. The impact of his theories can be seen in the technologies we use every day, from smartphones and GPS systems to medical imaging devices and renewable energy sources. Einstein's ability to think creatively and challenge established norms serves as a model for scientific inquiry and innovation. His relentless curiosity and willingness to question the status quo have inspired countless scientists to explore new ideas and push the boundaries of what is possible. Einstein's work reminds us of the importance of embracing uncertainty and exploring the unknown in our pursuit of knowledge. The implications of Einstein's theories continue to resonate in contemporary scientific research. In recent years, advancements in technology have enabled scientists to test and verify Einstein's predictions with unprecedented precision. For example, the detection of gravitational waves by the LIGO Observatory in 2015 confirmed a key prediction of general relativity and opened a new era in astronomy, allowing scientists to observe cosmic events in an entirely new way. The ongoing exploration of quantum mechanics, driven by insights from Einstein's work, has led to the development of quantum technologies that hold promise for revolutionizing computing, communication, and sensing. Quantum computers, which leverage the principles of superposition and entanglement, have the potential to solve complex problems far beyond the reach of classical computers. Quantum communication systems offer unprecedented levels of security, while quantum sensors provide unparalleled precision in measuring physical quantities. Einstein's legacy also extends to the field of cosmology, where his theories have provided a framework for understanding the large-scale structure of the universe. The expanding universe, described by the Friedmann equations derived from Einstein's field equations, forms the basis for the Big Bang theory and our understanding of cosmic evolution. Observations of the cosmic microwave background radiation and the distribution of galaxies have confirmed key predictions of general relativity, deepening our understanding of the universe's origins and future. The pursuit of a unified theory that reconciles general relativity and quantum mechanics remains one of the most significant challenges in theoretical physics. While Einstein's quest for a theory of everything was never realized in his lifetime, His work continues to inspire efforts to bridge the gap between the macroscopic and microscopic worlds. String theory, loop quantum gravity, and other approaches to quantum gravity build on Einstein's insights, seeking to develop a coherent framework for understanding the fundamental forces of nature. Einstein's influence extends beyond the scientific community, shaping cultural and philosophical discussions about the nature of reality and our place in the universe. His work has inspired artists, writers, and thinkers to explore themes of time, space, and the interconnectedness of all things. The iconic image of Einstein, with his wild hair and playful demeanor, has become a symbol of genius and creativity, embodying the spirit of inquiry and the pursuit of truth. As we look to the future, the lessons of Einstein's life and work remain relevant and inspiring. His commitment to scientific exploration, his willingness to challenge conventional wisdom, and his dedication to understanding the mysteries of the universe serve as guiding principles for the next generation of scientists and innovators. In conclusion, Albert Einstein's contributions to science have had a profound and lasting impact on our understanding of the universe. His theories have transformed the fields of physics, chemistry, and beyond, influencing the development of technologies that shape our daily lives. Einstein's legacy continues to inspire scientific inquiry and innovation, challenging us to explore the unknown and push the boundaries of human knowledge. As we continue to unravel the mysteries of the universe, we are reminded of the enduring power of curiosity and the pursuit of understanding that Einstein embodied.